O'Hare International Airport, Chicago. An airliner is being prepared for a trip to Frankfurt, Germany. A pilot is briefed for the flight. Captain Klaus Eidner of Lufthansa Airlines and his crew and passengers will fly east across 6 time zones, almost 1/4 of the way around the Earth. 5:15 p.m. Chicago time, the giant 747 airliner takes off. The jet age has brought high-speed travel to all parts of the Earth. This is especially significant for planes on east-west routes. Because of the Earth's rotation and the speed of the airplane, time will appear to pass much faster for the crew than for people on the ground. Their night will be drastically shortened. The plane has been in the air over 5.5 hours when the first light of dawn appears on the eastern horizon. It's midnight Chicago time, but in homes in Ireland below the plane, the clocks read 5 a.m. The airliner has been cruising at 650 miles an hour, but according to the clock, it's eating up time nearly twice as fast because of the rotation of the Earth below. The crew prepares to descend into the gray clouds blanketing central Germany.
431, you are cleared via overhead bus, Abba Blue 1 to Frankfurt, maintain flight level 370, report bus.
Captain Eidner contacts air traffic control in Frankfurt.
Via overhead bus, Abba Blue 1, flight level 37.
Is given data on visibility and wind velocity and landing instructions. The plane lands on schedule, a little over 7 hours after leaving Chicago. The plane's crew is finishing a 4-day round trip. They've crossed many time zones. Their patterns of eating and sleeping have been disrupted. Back in Chicago, it's the dead of night, and most people are asleep. The time there is 1:30 a.m. But in Frankfurt, it's a new day, and people are going to work. The time here is 7:30 a.m. But what time is it for Captain Eidner? What time is it for his body? We live in a world structured by time, run by mechanical clocks, 60 seconds to a minute, 60 minutes to an hour, 24 hours to a day. We eat, sleep, and work in cycles established by clocks. We march to the rhythms of clocks. But the clocks we have built are not the only keepers of time in our world. There are nature's clocks. The rising and setting of the sun gives us the 24-hour cycle of day and night. The rising and setting of the moon creates the rhythm of high and low tides every 24 hours and 50 minutes. The Earth's orbit around the sun provides the rhythm of the year, seen in the passage of the seasons and the changes they bring. All of these natural cycles have an effect on animals and plants. The most influential cycle is the alteration between light and dark every 24 hours. During the daytime, certain species of animals are active. Plants also are active, producing food by photosynthesis. At sunset, the shift changes. Other animal species become active, and plants enter a rest phase. Rhythms of activity that correspond to a 24-hour cycle are called circadian rhythms. Circadian is derived from Latin and means about a day. But do circadian rhythms of activity persist if organisms are taken away from the day-night cycle? This bean plant has been removed from its day-night exposure and is now kept under constant light. Time-lapse photography shows that for several days, its leaves continue to move up in the day and down at night. This shows that in the bean, circadian rhythms appear to be controlled internally. Dr. Beatrice Sweeney of the University of California is working with a one-celled marine organism called Goniolax. Dr. Sweeney has found a circadian rhythm of photosynthesis in these cells by measuring the amount of oxygen they produce at different times of the day. The rhythm persists even when the goniolacs are kept in constant light. So, even in single cells, circadian rhythms appear to be internally controlled. But what about more complex organisms, such as animals? Dr. Frank Brown of Northwestern University has been investigating rhythms of activity in a variety of animals. Much of Dr. Brown's work has been done with fiddler crabs. The color of these crabs follows a circadian rhythm, changing from day to night. During the night, the crabs are a light color. In daytime, they're dark-colored. But is the difference in coloration merely because sunlight strikes the crab, or is it controlled internally? To answer this question, crabs from the Atlantic coast of the United States are flown to the Pacific coast. They are transported 3 time zones away from their habitat. The following day on the East Coast, the rising sun lights the beach, and the fiddler crabs begin their daytime activity. They show daytime coloration as they scatter about the beach in search of food. On the West Coast, it's still dark. Sunrise is 3 hours away. The East Coast crabs have been kept in complete darkness in a laboratory. Now they are removed. They show daytime coloration. Their bodies are still responding to East Coast time in rhythms that will persist in continuous darkness. We might say their coloration is maintained by an internal biological clock. If animals have biological clocks, can they be reset? Dr. William Keaton of Cornell University is experimenting with homing pigeons to find out. The pigeons have been kept isolated in a room with lights that go on at sunrise and off at sunset. Their day corresponds exactly to the day outside the building. Now, half the pigeons are moved to a separate room where the timer is set back 6 hours. This means the lights go on 6 hours later than they do for the control group. Dr. Keaton calls this second group of pigeons the clock-shifted group. Their day starts 6 hours late. The birds are left in the clock-shifted room 5 or 6 days. Then the control group and the clock-shifted group are put in portable cages and removed from the laboratory. They are taken to a field 25 kilometers away, where they will be released to find their way home again. Red tape identifies the clock-shifted birds. It is 2 p.m. One by one, the pigeons are released. The pigeons orient themselves to the attitude of the sun in choosing a heading for home. For the control group, the sun is in its 2 p.m. position overhead. But the clock-shifted birds interpret the sun to be in its 8 a.m. position in the east. The control group, shown by the black dots, flies in the direction of home. The clock-shifted pigeons, shown in red, fly in the wrong direction, about 90 degrees to the east of the control birds. Pigeons from the control group begin to arrive back at the laboratory within an hour, and all of them have returned by the end of the day. For the control group, the sun is where it should be in the sky, so they can get their bearings and return home quickly. The day passes, and still there is no sign of the clock-shifted pigeons. The next day, the clock-shifted birds arrive, many hours behind schedule. They misinterpreted the position of the sun in the sky. Their internal clocks were time-shifted. This shows that biological clocks can be reset. But where are biological clocks located? Research with insects gives a partial answer. No single organ or gland has been found that controls all biological rhythms in animals. But Dr. James Truman of the University of Washington is experimenting to find out whether or not the clocks are located in the brain. He works with the pupae of two different species of moths. The adults of these two species normally emerge from their pupal cases at different times of the day. Dr. Truman exchanges brains between pupae of the two species to see if this will change the time of emergence. He uses insects for this experiment because their respiratory and circulatory systems are open. They function independently from the nervous system. Even if the brain is removed, the insect continues to live. This exchange of brains takes place between a robin moth, which normally emerges in the morning, and an oak moth, which normally emerges at dusk. The brains are transplanted into the abdomens of the pupae to ensure that they are isolated from the rest of the nervous system. The pupae with transplanted brains and a control pupa of the oak moth type are connected to a mechanical device that records the rhythms of their movements. Normally, the robin moth in the foreground would be active at this time of day. However, the oak moth is active instead. The rhythms of activity have been exchanged between the two species. The three moths emerge on the same day. In the morning, the oak moth emerges. Normally, it would emerge at dusk. But now its activities are governed by the robin moth's brain. Then at dusk, the control moth emerges. It's an oak moth with its own brain, appearing right on schedule. In a few minutes, the robin moth emerges. Normally, it would come out in the morning, but the oak moth brain transplanted into it has caused it to emerge many hours later. This experiment shows that in these two species of insect, biological clocks are located in the brain. Human beings have internal clocks too, and our bodies show changes that correspond to daily, monthly, and yearly cycles. These help explain how we act and feel. For example, eating a large meal first thing in the day and lighter meals later is less likely to cause a gain in weight, because the metabolic rate in humans is generally highest in the hours after awakening. Some individuals are active and alert first thing in the morning. This may be linked to the cycle of body temperature. When our temperatures are higher, we seem to have more energy. When our temperatures are lower, we are likely to be listless, even though it's mid-morning and there's work to be done. The day passes, and late in the afternoon, a burst of activity may begin, even though the clocks say it's time to stop working and go home. Our internal clocks are still at work at night, dividing our sleep into cycles of dreaming, deep sleep, and restlessness. What would happen if we could remove ourselves entirely from the mechanical clocks of our world? Dr. Andrew Algren of the University of Minnesota is conducting an experiment to see how his internal clocks respond to isolation. He's going to spend 3 weeks in a soundproofed, windowless room, cut off from the outside world, removed from the cycle of day and night, the usual daily round of human activities, and from all mechanical clocks. He wants to find out what kind of rhythms his body establishes when it's running free. To keep his mind occupied, Dr. Algren plays music, reads, and catches up on his research work. He keeps close track of his mental condition. By electronic signal, he lets his research assistants know when he is exercising, taking measurements of his bodily functions, sleeping, eating, and working. All this information is needed in order to determine his different bodily rhythms. During his period of isolation, Dr. Algren's rhythms run on slightly longer days, from 25 to 28 hours. Left to run free, the human body tends to shift into a longer day. Bodily rhythms tend to drift apart when not synchronized by a regular daily schedule. Dr. Mariana House lives in Austria, and she's flown to the United States to visit her son. She's experiencing jet lag because her circadian rhythms are not synchronized to the day-night cycle in the Midwestern United States. At regular intervals in the day, wherever she may be, Dr. House records her own blood pressure and temperature. For several days, as her body adjusts to the new day-night cycle, her blood pressure rhythms fluctuate. This is a clue to the changes her internal clocks are undergoing. Dr. House enters the data in a log she's been keeping for 8 years. Her son is Dr. Erhard House of the Ramsey Medical Center in St. Paul, Minnesota. Using the 8 years of records his mother has kept on herself, he determined that she has a number of cycles, hourly, daily, monthly, and yearly. These data also show that it takes days to several weeks for the body's rhythms to fully adjust to a new time zone. This information shows that there is no simple answer to the question, what time is it for your body? Individuals have their own rhythms and cycles controlled by their own internal clocks. For this reason, airlines recognize the importance of biological rhythms that affect the physical and mental health of their crews. These men undergo frequent tests of their mental and physical condition. Pilots must be in excellent health because they are responsible for the lives of hundreds of people on every flight. Yet they constantly fly back and forth across time zones, which throws off their internal clocks. Airline physicians, such as Dr. Helmut Bach, educate pilots about the effects that bodily rhythms have on their performance. Because people do have internal clocks, it's important to know how the clocks work and how they influence behavior, especially under conditions of stress. These 2 mice have been put into a stress situation. One mouse has been clock shifted 12 hours. Its frantic behavior shows that it responds poorly to stress. The other mouse, whose internal clock is normal, stays calm. People subjected to shifting work schedules also undergo changes in their biological rhythms. This can lead to lower efficiency and increased accident rates. Doctors may find themselves in emergency situations at all hours of the day and night, and their performance can be affected. One doctor may work efficiently at a 3 a.m. surgery call, but another may not do so well. Knowledge of internal clocks may help hospitals schedule emergency work and duty hours, and may even help save lives. Knowledge of biological cycles in plants can also be put to use. Dr. Willard Kukuri at the University of Minnesota is conducting studies to find ways to apply this knowledge. One such study shows how weeds react to herbicides, depending on the time of day when the chemicals are applied. These velvet leaf plants are given measured amounts of herbicide, each at a different time of day. New leaves on the plants are removed and weighed to determine growth rates. It appears that some plants exposed to the herbicide may be more susceptible at certain times of the day than at others. Field tests show similar results and suggest that greater crop yields and more energy-efficient farming could result from the application of knowledge about biological cycles in plants. Laboratory analysis of human blood reveals rhythms that can help doctors decide at what times medication should be given. Blood is analyzed for white blood cell count, hormone levels, mineral concentration, coagulation rate, and other data which establish biological rhythms for each individual patient. This knowledge can help doctors tailor treatment to the individual rhythms of their patients. For example, in chemotherapy for cancer and treatment of high blood pressure. Studies of internal rhythms in humans and other organisms are yielding many beneficial applications. This is the new science of chronobiology, the study of internal clocks and biological rhythms. It is becoming an important part of all the life sciences as we begin to understand the vital roles played by biological clocks. We now realize that our lives are great continuing webs of interlocking rhythms. From conception to death, we are all clock-driven creatures.